Okay, hi everyone. My name is Harry Bray. I'm at George Mason University. I'm talking today about volume entropy rigidity for convex real projective manifolds. This is the introductory part one. All of this is based on joint work with Elisimi Adeboye and Dave Constantine, who are at Wesleyan University. Okay, so first, let's talk about convex real projective structures. If I ever write CRPS, that's what I mean. So I'll introduce them via their natural metric. So the Hilbert metric is defined on a properly convex domain, denoted omega, in real projective space. So what do these words properly convex mean? So let's just think RP2. So we're looking at the space of lines through the origin in R3. And omega is an open subset of that space. So omega could be like the first, omega could be some cone over some blob like this, right? Okay. Omega could look like that. Omega could be, I'll draw something else now. Omega could be all of the lines whose let's give these names X, Y, Z axes. So we could look at all of the lines whose Y coordinate is non-negative. And then all of those lines are, or let's say all of the lines whose Y coordinate is positive, and that gives you another open subset of real projective space of RP2 in particular. So those are, possible subsets. And then to be properly convex means that there exists an affine chart in which your set is bounded. So it means if you could take some slice, so going back to the cone that we saw over the blob, right, there is a slice, if the cone looks kind of like this, there's a slice of this cone in which this intersection is bounded. So we could pick it up and paste it on the page, and we will often do this and conflate a properly convex domain omega with its chart. But this boundedness is just the definition of proper. Proper is that you can find an affine chart, you can slice this thing up in that affine chart and get something which is bounded. And then convexity is just convex in some such affine chart, right? There is an affine chart in which you get something bounded and convex like this guy. Since omega is the cone, you don't want to take your slice to be something over there that contains something non-convex. You just want something, you want a good affine chart in which you get something convex. So that's what a properly convex domain is. Subset of projective space, open subset of projective space. You take a slice, paste it on the page, you get something bounded and convex. So this is the kind of space where it makes sense to define a Hilbert metric. So let's talk about what that guy is. So now we're starting with some properly convex domain, and we want to put the Hilbert metric on it. So now again, I will hereafter conflate omega with its representation in an affine chart in which it's bounded. And I take 2 points, X and Y. I want to define a distance between them. So what I'll do is there's a unique line in this affine chart determined by these 2 different points, X and Y. And if they were the same, we would just define their distance to be 0. But if they're different, then we get this unique line. You take A and B to be the endpoints of that line intersected with the boundary of omega, which we can reach because omega is bounded. And then this distance is 1/2 of the log of the cross ratio of these 4 points in order, where more specifically, the cross ratio is the ratio of is the ratio of distances here in this affine chart, and it'll be invariant under choice of affine chart, so it won't matter which affine metric you care about. So this is just going to be, some Euclidean metric. So we've got the distance between A and Y, and the distance between X and B. These are the larger distances. So everybody's going to be represented in the numerator and the denominator here. And you'll put the larger distances on the top and the smaller distances on the bottom so that you'll get a ratio that's larger than 1. Okay, so the larger distances, A minus Y, X minus B, divided by the smaller distances, A minus X, Y minus B. So it's not necessarily obvious right off the bat that this gives you a metric. The triangle inequality is something to prove, but it does give you a metric. One thing, so some properties of this metric. It's well defined. It doesn't depend on the choice of affine chart. The cross ratio is because the cross ratio is a projective invariant. So you can slice omega any way you want. And it's also, for the same reason, preserved by projective transformations. The metric is, in general, only Finsler. That means that it's not necessarily Riemannian. It may not come from an inner product. So angles are not necessarily defined. Geodesics, by design, are straight lines. It's not necessarily a space with unique geodesics. There can be other geodesics, but in the setting that we're thinking about today, geodesics will be unique. The metric has close relationships to the boundary by design. If the boundary is irregular or not smooth, then the metric also will not be smooth. Convexity of the metric similarly coincides with convexity of the set. So in the words of Ludovic Marquis, these metric spaces sort of feel like damaged non-positive curvature. They're not cat 0. They're not even cat k for any k, but they'll have a lot of properties resembling non-positive curvature. In the setting that I'm looking at today, they'll actually have properties resembling negative curvature. And lastly, they admit a natural volume form called the Hilbert volume. I'm not going to define what it is. It's not really necessary to know the definition, but just bringing it up because it will come up later in the talk. Okay. So a convex real projective structure on a manifold, say manifold M, is a quotient of some such properly convex domain omega by a discrete group of projective transformations gamma, right? So gamma is I mentioned that projective transformations preserve the cross ratio. So any projective transformations which preserve omega are therefore isometries of omega with respect to the Hilbert metric. So that's where this is coming from. So M is a quotient of such a properly convex set by a discrete group of projective transformations acting properly, discontinuously. So M could be, a compact manifold could be a surface of genus G, or it could have some cusps. It could have finite volume with respect to the volume form that I mentioned on the other page. Okay, so this is a hypothetical convex real projective structure. Do these things really happen? What could they look like? So one first example is the Beltrami Klein model for hyperbolic space. If you take your omega to be an ellipsoid, which I'll denote by a curly E, you can quotient out by a representation of your favorite hyperbolic group into SO(n)(1), and you can get, or a conjugate of that, depending on which ellipsoid you picked. And then this can give you, one of that, depending on which hyperbolic manifold group you cared about, it would give you a hyperbolic manifold. So in other words, this with the Hilbert metric, the ellipsoid, so the ellipsoid with the Hilbert metric is literally isometric to hyperbolic space. This is just another model for constant curvature -1 hyperbolic space. So if you were wondering about that factor of 1/2 in the definition here, this is carefully chosen so that the Hilbert metric gives you on the nose constant curvature -1 when you choose the ellipsoid as your properly convex domain. And I keep saying the ellipsoid because up to projective transformations, there's only one. Okay, so this is a first example now of a convex real projective structure on a manifold. It's the hyperbolic ones. So I'm kind of assuming that the people who have decided to watch this talk like those guys and know about hyperbolic spaces. And I hope you'll still listen if you don't love those guys, but and then you'll come to love them. But anyway, okay, so here's another example. So now let's take, let's realize the projective triangle as a slice of the first octant of R3. So slice of the first octant of R3. Okay, here's right the X, Y, Z axes. And now we can take a Z² group generated by two different diagonal matrices. So say lambda 1/λ² with lambda bigger than 1. So if we look at the action of iterates of G on the first octant of R3, right, the x-axis, it's rescaling, it's scaling in the x direction and the y direction, but projectively, these directions are then fixed. So projectively, these are fixed points. And in the z direction, same story. This is also a projective fixed point, but this z-axis is a repeller and the x and y axes are attractors. Since it's scaling uniformly in the x-y direction, every point on this, every direction here, right, is also projectively fixed. And then this z-axis is a repeller. So these are all invariant lines under the action of G. G is going to be acting by translation along these lines, projectively. Okay, and then we can add another guy, which inevitably commutes with G by making it diagonal. So now it could be like lambda, I don't know, I'm going to call them lambda, mu, and eta, and suppose their product is 1, and they're all chosen so that this picture looks how I want it to. So let's say the y-axis is repelling, the z-axis is neutral, and the x-axis is attracting. So then there will be these invariant conics under the iterates of H. And as we apply H over and over again, H, we will move points towards the x direction here. And so G and H commute, they generate a Z² group. And we can see a fundamental domain for this action, for instance, right here, where opposite sides are being connected by translation. So this is a quotient torus. So here's another example of a convex real projective structure that we already know. And indeed, if you put the Hilbert metric on the triangle, you'll get something which is quasi, you'll get that the triangle with this metric is quasi-isometric, though not isometric on the nose, to R2 with the usual metric. On the nose, it's isometric to R2 with a hexagonal norm, if you know what that is. All right, so these are some examples. One connection that I'll make. So as we noticed, the hyperbolic example, we started with an ellipsoid, nice and smooth. with this flat example, we started with a triangle, which has lots of lines in the boundary and it has singularities in the boundary. So in general, proved first by Benoit in the compact case and Cooper-Long-Tillman more generally, if M is finite volume, then the following are equivalent. The boundary is C1, so the M is the quotient of omega by a discrete group of projective transformations. So it's equivalent that the boundary is C1, omega is strictly convex, and the metric space is Gromov hyperbolic. So this is hyperbolic in the sense that triangles are thin. I'm not going to talk more about this kind of hyperbolicity, but you should imagine omega is with this metric is quasi-isometric. Yeah, I don't know. I won't. Maybe I won't say more about that. So hyperbolic in the sense that metric triangles are thin. Okay. So some more examples other than the ones that we've already. So we've seen through this type of geometry, we've seen some examples we've already known. We've seen R2 with quotientori. We've seen hyperbolic space. And now, what else is out there? Like, are there other non-trivial examples? Are there new geometries in these spaces? So suppose we're looking at a surface of genus G with n punctures, and we're looking at all the convex real projective structures on this. Obviously, this is going to be up to projective transformation. So this is, it's actually computable, the dimension of this moduli space. Goldman computed it without the punctures and Marquis with the punctures in his thesis. It's 16, so the dimension is 16G minus 16 plus 8N. So this is much bigger, right, than the Teichmuller space, which is dimension 6G minus 6 plus 2N. So these guys, right, so and this Teichmuller space, as we know, is sitting neatly inside of this space of convex real projective structures via the ellipse example, because the Beltrami Klein model, the hyperbolic example, right, is an example of a convex real projective structure. So there's plenty of non-trivial examples, right? There's a large moduli space of non-trivial examples. When the dimension is higher, the geometry is not necessarily deformable, but there are examples which are deformable. So Johnson and Milson applied Thurston's bending to n manifolds with a totally geodesic submanifold, where they do some bending along that totally geodesic submanifold to get non-trivial convex real projective structures. There are all sorts of Coxeter group constructions which are inevitably confined by the dimension due to, for instance, Katz-Wimberg, Marquis, and there's some ongoing work on this going to convex co-compact situations and so on. And then there's some specific three manifolds realized as not complements. So Cooper-Long-Tillman, Ballas-Marquis, Ballas are some names who have shown that they're deformable examples here. So there are plenty, there are interesting examples of convex real projective structures which are new and different. To give you a picture of this deformable, so here are some images of deformations of the infinity triangle group. This is part of a log M project mentored jointly with Giuseppe Martoni and Mitul Islam. The students, Marianne DeBrito, Marissa O'Gara, and Andrew Wynn are down here. But basically what this thing is right, so this is a fundamental domain for an infinity triangle group acting on different properly convex sets. So there's a parameter T which varies between 0 and infinity. This is omega, and these are all different omega T's. So this is I think this is omega 1. And then this one is omega 4. And each time by normalizing, there's always the same fundamental domain here, and then the group changes, and omega changes with the parameter. So there's this one parameter family of different Hilbert geometries associated to this particular quotient. Okay. So if we assume that n is at least 3, and that we're looking at a manifold which admits, so this is the dimension of the manifold, and we're assuming it admits a negatively curved metric of finite volume, then Mostow rigidity, so in finite volume, Mostow-Prasad rigidity, states that there is a unique hyperbolic metric of constant curvature equal to -1. There's a unique hyperbolic metric of constant curvature -1. So okay, so the question, a motivating question that I have here is, what characterizes this hyperbolic example in the space of convex real projective structures on N? So that's the motivating example. Now that we've kind of looked at this moduli space, and the theorem that I'm going to talk about today is going to be one answer to this question. So tune in for this next part to hear more about some answers to this question.